first thing I'm going to say, if you already saw the slide, is that we cannot manage what we cannot measure. All right, and we're talking about the management of health information, financial information, all different types of information, and we're talking about privacy risks. Usually we don't know what these risks are on a quantitative level. So that's kind of what a lot of this talk is about. So where is this talk going to go? It's going to have three different components. First, we're going to talk about how to model risks. Then we're going to talk about how to measure risks. And then we're going to talk about how to mitigate risks. Kind of similar to the N-cubed thing of the title. All right, so I want to start with what I call the faith that launched 1,000 ships. All right? So stop me if you've heard this story before. Back in the 1990s, there was a situation in which the governor of the state of Massachusetts ended up collapsing while giving a talk while on stage, and he ended up getting admitted to Massachusetts General Hospital, and nobody knew what happened to him. Well, there was a researcher at MIT at the time who ended up being my dissertation advisor, for full disclosure, who went off and took the hospital discharge data from the state of Massachusetts, in which you had all these things that occurred. So you knew the diagnoses, the procedures, when something occurred, the ethnicity of the individual, their meds. You had some demographics about this individual, such as the zip code of residence, the birth date, the gender. And then wrong direction. For $10, she went off and purchased the voter registration list from the city of Cambridge, where she knew the governor lived. Notice that in this data set you had the name of the individual, some other information, but you also have some demographics that look eerily similar to what we just saw in the last data set. All right, so when you cross these two types of data sets, this allowed for the re-identification of the governor, who was William Weld at the time. Has everybody heard about this story?
Yeah, it's in the...
It's a very famous story, right? For some of you. If you haven't heard about it, we can talk about it more later. So when the study was extended, one thing that was found was that when you took the combinations of these features, the zip code, the 5-digit zip code, the birth date, and the gender, that the famous statistic is that 87% of the United States was considered to be unique. Now, this was a study that was done back in 2000. The study was updated by Philip Gall in 2006. He said, maybe it wasn't 87%. Maybe it's closer to 63%. Regardless, that's a lot of people. So this actually has spurned what I call a phenomenon. And the phenomenon, as an example, is exemplified by the AOL case. So AOL back in 2006 ended up taking a lot of search query logs, and they ended up pseudonymizing all the users consistently. So they would just take the names and they would replace them with consistent pseudonyms. And then they would take the query, they would take the time of the query submission, and then they would actually say what the user did after they submitted their query. So which link did they click on? And the whole goal was to support information retrieval research. So they took data on about 650,000 customers, 20 million queries, 3 months of data, and they ended up putting this online. Now, let me give you a case study. This is user 4417749. They issued hundreds of queries. They issued queries like this. Numb fingers, 60 single men. We don't know if they were looking for 60 single men or single men in their 60s. Things like medical issues like hand tremors or dry mouth or nicotine effects. But they're also putting other things like their name or names in there, Arnold, places, Georgia, other things about Georgia, a particular county. Now, notice that what popped up at the end is a New York Times story. So these two journalists, Barbaro and Zeller, ended up taking the data that AOL put online and they ended up saying, oh, that's a really interesting person. It's this person. And they ended up calling her and they ended up validating it. So they ended up re-identifying Thelma Arnold and Dudley, which is her dog. You might have seen one of the things in there that said dog that urinates on everything. That's Dudley. So this became a big story to play out the game. In July 2006, this was when they put the data online. Barbaro and Zeller published their story in August of 2006. A couple weeks later, AOL removed the data set. In late August 2006, the CTO of AOL resigned. The researcher and the project manager were dismissed. The project manager is now faculty at a university in Illinois, but I won't tell you where. And in September of 2006, a class action lawsuit was filed. Okay? That class action lawsuit ended up being settled for about $10 million, and you thought we would have learned, but then Netflix ended up publishing a lot of their pseudonymized movie review data. And so Arvind Narayanan and Vitaly Shmatakov down at the University of Texas ended up doing a study that said, hey, the movie reviews are relatively unique, and you've got some identified data sitting over in the IMDb repository. I bet we could use these to re-identify people. Whether or not you could actually do that, that's debatable, but what it ended up leading to was Netflix settling, again, a class action lawsuit that ended up being brought about by the same lawyer who did the AOL lawsuit. And Netflix ended up taking their data offline, and they canceled the Netflix Challenge version 2. Okay? So the reason why it's become a phenomenon is that you're going to find all these types of studies in uniqueness. And so it doesn't take many things to make you unique. And really all you have to do is insert your favorite feature here. So people have done studies with demographics. We've done studies with diagnosis codes. Xiaofeng has done studies with SNPs. We've got location visits, movie reviews that we just talked about, the familial structures of people, search queries. There's been a lot of work by Lars Backstrom and also by Vitaly's group on social network structures. So the question is, is this is this the limit? Are we going to see more? Chances are we're going to see more. So it's a phenomenon. It's continuing to play out. Okay, now coming back to healthcare. So 1996, the Health Insurance Portability and Accountability Act came out. And so I call this the elephant in the room. The whole point of HIPAA was to resolve inconsistent state laws, and it was supposed to help the sharing of health information between disparate entities. Now, in the context of HIPAA, they defined this notion of what's called a covered entity. Okay? Now, this is somebody who is acting on behalf of the patient. So it's healthcare providers, it's healthcare clearinghouses, it is somebody who is helping in healthcare operations. Google, Microsoft, they're not involved in all of this, so we're not going to talk about them today. Now, they define in HIPAA what's called protected health information, or PHI. If you work in the medical world, you hear PHI all the time. Now, this is data that is explicitly linked to a particular individual, or it's data that could reasonably be expected to allow individual identification. Now, I'm including you into reasonably, okay? If you go off and you ask a lawyer, are there any lawyers in the room? Oh, where's Fred? If you go off and ask what reasonable is, you're going to get a shrug of the shoulders, and they're going to say, oh, it's got to play out in the courts. And so this notion of reasonable has not been defined yet. So this is what we just said. Now, HIPAA, the interesting thing is that the privacy rule and the security rules of HIPAA were promulgated by different groups that actually passed the regulation. So the regulation was passed by Congress in 1996. They did not actually get around to passing the privacy and security rules. When Bush came into office, he actually said, you guys are going to pass the privacy and security rules, which was a complete shocker to a lot of people. But it ended up falling to Health and Human Services, not Congress. So there's actually conflicts between what is known as the common rule and the privacy rule. That's not the scope of today. But what I will say in the context of the privacy rule is that it permitted secondary data sharing without patient consent. And the way in which it did so was two different ways. One is what's called limited data sets, and the other one is what's called a de-identified data set. And underneath the identified data sets, they actually give you two different ways to achieve this goal. One is called safe harbor, the other one is called expert determination methods. Now, when talking about these methods, I want you to recognize something. We care more, we don't just care about the uniqueness of data. We actually care about the broader aspect in terms of how many people could a particular record correspond to. So, now, let's move towards measuring, because otherwise I'll run out of time. So what exactly is a limited data set? Limited data set, first of all, you have to recognize, requires a contract. So basically, as a recipient of the data, you are signing your life away in blood to get access to information about patients. And you're allowed to use this information, but you're not allowed to attempt to identify or contact the individuals who are the subjects. And you're only allowed to use it for the purposes that you specified. Now, the data owner, or the person who's sharing the data to you, they're going to remove a certain set of attributes. It's actually 16 enumerated attributes. They have to remove patients' names and initials. They have to remove identifying numbers like phone numbers or social security numbers. They have to remove anything with respect to websites if it relates to the patient. They have to remove biometric identifiers such as fingerprints, voice prints. DNA is not designated as a biometric identifier under HIPAA for various reasons. Now, the owner is allowed to include these types of things. So they can have dates of birth, dates of death, dates of service, and they're allowed to have geographic information, such as the town, the zip code, and the county in which the individual resides. Okay, so that's the definition of a limited data set. Safe harbor is kind of so now we're shifting into de-identification land. This is outside the scope of contract. This is data that you can share without any controls, all right? This requires 2 additional attributes to be removed, one of which is anything that with respect to geocodes that imply that there's less than 20,000 people in that group, and it requires the removal of all dates except for a year, and any age or anything that implicates the patient's age as being over 89. This is known as a cookbook approach. Okay? This is a policy that a bunch of people sat down in a room and they said, hey, what did that person do when they re-identified the governor of the state of Massachusetts? Oh, they used dates. Let's remove dates. Oh, they used 5-digit zip codes. Let's remove those 5-digit zip codes. So they also put this little catch-all in Safe Harbor that says you have to remove any other unique identifying number, characteristic, or code. What does that mean? Basically means that if the person who's holding coded data can identify that patient, then it's considered to be an identifier. Now, this does not mean that if the data is unique, it's going to be protected under Safe Harbor. It's not. Really what this means is things like barcodes or clinical case IDs that were not explicitly designated in their list of 18. So, okay, we've got limited data sets. These basically go to researchers who sign their lives away in blood. And you've got the Safe Harbor data sets that can go to the public. So one of the things that we recently did was we revisited some of these studies on the attacks at demographics, and we said, look, imagine you take the identified data and you shove it through these 2 policies. You go through Safe Harbor and you go through limited data sets. What's the difference in the risk in terms of how many people could be identified? So we actually went back to the US Census count data, and I'm not going to talk about this today, but I have some slides if you want to talk about it. One of the problems with using census data and limited data sets is that limited data sets say you can give out the date of birth for a patient, but census counts don't tell you counts with respect to dates of birth. They only give you counts with respect to like the year of birth. So we have to disaggregate this data a little bit. What we're using is not perfect, but it's going to give you some clue into how risk changes. So as a case study, here's the state of Tennessee. What you're looking at here on the x-axis is basically the group size. So for all the people in the state of Tennessee, given the parameters or the features about that individual that were allowed to go out given the policy, so this is a Safe Harbor policy. I call it Safe Harbor-like because we removed all zip codes here. We just did the aggregation to the state level. So this is Safe Harbor. This is and what you see on the y-axis is the fraction of the state's population that would be in a group of this or less. Okay, so this is the number of people that would be unique. It's really small in the context of Safe Harbor. Now, what you see in the blue line, this is limited data sets. It starts at about 33%. Okay, by the time you get to a group size of about 33, everybody's in a size of group 33 or less. Whereas in the context of Safe Harbor, that number isn't really hit until about this point, which is about 20,000. Now the reason why I bring up that 20,000 is because that's the magic number that they put in Safe Harbor, right, with respect to geocodes. They said you can't share that data if it corresponds to a population of 20,000 or less. And we said, well, okay, well, how many people would be identifiable in that context? And basically it says, well, theoretically about 30% of that population would be designated as at risk for identification. Is that really what the federal government meant to imply? We don't know. So we actually did this study for all of the US states, and these are several points at which the study was done. So this is uniques, groups of size 3, groups of size 5, and instead of fraction, this is now percent identifiable because the numbers got too small. But basically you see like about 0.001% of most states have people that are unique. What's important to recognize is that it's not zero. Okay? So there's always going to be this notion of inherent risk in sharing this data. So this is Safe Harbor on the left, and notice that the numbers jump significantly when you consider limited data sets, and I'm truncating here, but the number that you see at 10, group sizes of 10, is about 90% on average. So these points correspond to about all 50 states. Okay. Now, the other thing that you have to question is, what do you actually mean by risk? A lot of people use different metrics, or at least we've defined different metrics that people use to say how risky is a data set to share. I quote Khaled El-Imam on this, who's at the University of Ottawa. He basically defined 3 different risk models, one of which he calls the prosecutor risk. Okay? Prosecutor risk says, look, imagine I give you a subpopulation. Okay, that's the small f right here. So these are all the people who are Asians living in Bloomington who are of age 20 to 25. Okay? And this is the sample set that the university's medical school is going to disclose. Okay? This basically says that how well could a person take any particular record in this subpopulation and identify it in the context of the larger population from which it was derived with the same demographics. Okay? So this is the people who were in the study. These are all the people in the state or in this region in Bloomington that had the same demographics. The journalist says, I don't know if that person was in the study or not, but I do know all the people out here, so how well could I have a chance of identifying one of the people in the population from which they were derived? The marketer risk is what we're going to be talking about mostly. Marketer risk is kind of like the how many people could you identify in total, all right? And so that considers all these different groups, and it says, imagine that I tried to assign each person in this subpopulation to the population from which they derived. What's the expected number of people that I would correctly identify? Okay? So people call this the marketer risk. I say you should probably consider this to be the class action lawsuit risk. Because this basically says that if there's an identification, how many people could actually come and sue you and actually have grounds for doing so. So one of the things that we did in our analysis recently is we looked at a trust differential. We said, look, imagine you look at how many people would be identifiable underneath the context of limited data sets and normalize that by how many people will be identified in safe harbor, because this is guaranteed to be larger than this. How much worse would it be? In other words, how much more are you trusting the people who sign their life away in blood than the people who are in the general public that get access to your data sets? And so as an example of uniques, what we see is that in the state of Delaware, that risk factor increases by about 1,000-fold. Now, there are small sample statistics in this context, okay, so keep that in mind. But the thing to recognize is that the risk changes per state. So in Delaware, we've got a risk change of about 1,000. In the state of Tennessee, we've got a risk change of about 2,300. And in Illinois, we had a risk change of about 65,000. Okay. So people say, well, maybe that's just an artifact of the small numbers. When you look at the situation of 20,000 or less, here's where things get really interesting. State of Delaware's risk doesn't change, actually. So what's the difference between these policies? Now, that's not always the case. State of Tennessee, we're still increasing by a risk of about a factor of 8. Illinois is increasing by a risk of a factor of 37. Okay? So this leads me to what I talked about in the abstract, which is a paper that Paul Ohm published earlier this year. Now, Paul's a lawyer at the University of Colorado, and I'm not going to begrudge him at all, very smart guy. But Paul publishes this paper, and he calls it Broken Promises, Responding to the Surprising Failure of Anonymization. He says a couple things. First of all, he says, these notions of re-identification or de-anonymization of individuals, these can be done with astonishing ease. That's a claim that he makes. The second thing he says is that by understanding what all the computer scientists have done, he basically is saying we've made a mistake. And it's a fundamental misunderstanding in that we have falsely assured people privacy based on what we've been doing. Okay? And he also says that this mistake pervades nearly every information privacy law, regulation, and debate, yet regulators and legal scholars are basically not addressing that issue. Okay? So these are a bunch of claims, and we can start to test these claims. Because even though I'm one of the people who published a lot of the re-identification studies, I actually think that they're a lot harder to do than what has actually been perpetrated or shown in the literature. Not perpetrated, just published in the literature. So the reason why I say this is because, but, as I'm just alluded to, there's a really big but. This notion of distinguishable is not the same as identifiable. Okay? As an example, and I call this the central dogma of re-identification, I could give you a bag of de-identified DNA, and I say, look, this is 100 people's DNA sequences. and then I give you a bag of names, and I say they were all at the same hospital, okay? I say, tell me who corresponds to whom, all right? Chances are you wouldn't be able to do it with any guess better than random. And the reason why is because you need to have a linkage mechanism. So you basically need 3 necessary conditions in this context that you need to satisfy. Now, some people would argue, okay, this linkage mechanism might come about in the future. We're looking at things a little bit more practically and saying, are the policies sufficient at the present point in time? Could you actually define these linkage mechanisms? So one of the reasons why I ended up at Vanderbilt was back in 2004, they initiated probably what's now the largest DNA bank tied to electronic medical records in the United States. And this started with a very large community consultation process. Everybody knew we were doing this. It was a very well-designed effort. Currently what we do is we take all the electronic medical records, about 1.5 million people, we de-identify them in accordance with Safe Harbor, and we update these on a weekly basis. At the same time, we take leftover blood from laboratory tests. This is a consented environment. And we're capturing about 50,000 people per year, and we're taking out the DNA, and we're doing correlation studies between the clinical data and the genomic data.
But you said it was consented. Who consented?
All the patients. It's done in an outpatient setting. So the...
So it wasn't enough for the lab to consent? Like,
no, you actually have to do it before you actually see your doctor.
So they know that their blood will be...
Oh, yes.
Yeah, okay.
Yeah, you definitely know that you're becoming a part of the DNA data bank at that point.
Is the consent a requirement of receiving treatment?
The consent is tied to the waiver to treat form. Thanks, Don. Yes. I will say that that was constructed before I got there, and I was not a part of it, so you can debate the merits of it amongst yourselves. Now, what we basically do is we allow investigators to come in, and they can search for cases and controls through basically an indexed version of the electronic medical record system. We give them scrubbed copies of the medical records. At that point, they can do some data analysis, or they can say, now I want to do sample retrieval of the DNA, at which point they can take that information, they can genotype it themselves, and then they can do the genotype and phenotyping relationships. Any genotyping that they do goes back into our database so that we don't have to replicate that every time somebody comes in. A lot of people say, oh my God, how do you actually accomplish this? One of the things I'll say is that this was an institutionally funded project. It was about a $10 million investment from the medical center, and it was also sanctioned by, signed off on by the Office for Human Research Protections at HHS underneath the designation as non-human subjects research. Now, that basically meant that the samples and data are not linked to identity, and everything that's done is conducted with IRB and ethics oversight for every individual study that's done with the DNA data bank. So if you come in and you want to do a study with diabetes, you have to get approval to do that study with diabetes, and every time you log into the system, you use that approval ID. If you want to now do a study with I don't know, telangiectasia, or if you want to work with cystic fibrosis, you have to do a completely different study ID. Yeah?
Regarding the consent, are you guys using open consent?
No. The patient, all the data is used in a de-identified context. So we actually tell them it's not going to be identified. Now, de-identification has a specific definition. It doesn't mean that the data is anonymous, right? So that was one of the concerns I had with Paul's paper that said failure of anonymization, which is a whole different issue. But a couple years ago, we took federal funds. We took federal funds from the NIH to become part of a consortium that's known as the Electronic Medical Records and Genomics Network. That includes us, University of Washington, specifically Group Health Corporation of Puget Sound, the Mayo Clinic, Northwestern, and the Marshfield Clinic of Wisconsin. Basically, they said, take data that you already have in your EMR systems and start doing those correlation studies. Now, the condition of funding, though, is that you have to contribute de-identified genomic and all your phenotype data into what's called the database of genotype and phenotype at the NIH. Okay? And the reason why this is the case is because the NIH, back in 2003, instituted what's called a data sharing policy. They said that it's their philosophy that data should be made as widely and freely available as possible, And that at the time, this was in 2003, anybody who got at least $500,000 in any particular year of a study was going to have to figure out how to share their data, or before you submit your grant, you got to explain why you can't do that. And it was in this policy where they said the data has to be shared in a manner that's devoid of identifiable information. How did they define that? They went back to HIPAA. They basically went back to the safe harbor model. In 2006, they revised their policy for genome-wide association studies, and they said, we don't care how much money we give you. You're giving us the data. Okay. So that's why I went to
I think
management.
it should be strictly bigger than 0.
Oh, no, they don't necessarily have to give you money. It could just be a contract in which they say you're going to be able to use data, or you're going to be able to generate data. As long as you have a contract with them, you still have to give the data. Yeah, everybody always brings that up. But I appreciate that you brought it up. So, what you've been seeing so far is what I would justify as a worst case scenario. That is uniqueness or distinguishability of a population. I've given you a couple case studies in which identifications were done, but they were few and far between. So the question is, how would you use certain types of data to identify people? I'm not going to talk about genomics today. I'm not going to talk about the genomic data. That's a different issue. I'm going to talk about the simpler way. How could you use demographics? So there's a lot of different ways to get access to demographics. There's birth registries, there's death registries, there's marriage registries, and there's other types of lists that may exist out there. And what's in vogue is really coming back to the voter registration databases. And the reason why we're going back to voter registration databases is that when we did a review of the literature, every single computer science paper that talks about the re-identification concerns or identifiability concerns, they cite the original Sweeney paper on using voter registration data to re-identify people. And we were like, is that really possible? So we went back to each of the states, each of the US states' electoral commissions, and we asked them, what do you share? What do you give people? And we actually did this during the 2008 election. We were really surprised they actually responded to us. We said, what information you share, who are you giving it to, how much does it cost? And so then we put it through our little policy machine, and we said, given the data in safe harbor and limited data sets, how well would I do in identifications or potential for identifications? Now, so this is a study that we did for the eMERGE network. So these are the 5 states in which the medical centers resided. So here's Illinois. Notice that you don't get ethnicity, but you get gender, you get date of birth, and it costs about $500. Notice the state of Wisconsin. Costs $12,500 to get their voter registration data, and you don't get date of birth, you don't get the gender, you don't get ethnicity, you don't get phone numbers, you don't get any of that stuff. Minnesota, it's $46. They have a restriction that says you can only use this data for political purposes only. So if you use it for re-identification purposes, then you are violating the law. And you don't get date of birth, you get year of birth. You don't get the gender of the individual, though that may be inferable from the name. Basically what you see is that it's all across the board, and it's variable. So when you actually go back and redo that linkage study that we did, or the identifiability study in limited data sets, this is what happens when you start tying it to voter registration data. The worst case scenario drops down significantly. Usually, on average, it's a factor of 3. Some cases, it drops all the way to 0. An example of why that's the case is that Illinois, as I said, doesn't necessarily give you dates. It gives you years. And so this is basically the identifiability of the limited data set. This is the limited data set tied to voter registration data. This is Tennessee. Notice Tennessee doesn't change at all. Okay. So we then started asking the economic question, which is that if you're going to try to identify someone, chances are you're going to have to pay to do it in some way. How much did it actually cost you to do an identification? So this is using that class action lawsuit risk model. This says these are really bad situations. These are how many people would be at risk in the state of Virginia, New York, South Carolina, and how much would it cost to do a re-identification. In this context, it doesn't cost you anything, and you get a lot of people. But in the state of Wisconsin, the state of West Virginia, the state of New Hampshire, you don't get to identify a lot of people, and it costs you a lot of money. All right? It costs you upwards of $800 per person to identify. if you look at the safe harbor model, the publicly available data, oh, I can't see this very well. Basically, these are the same states. Again, it doesn't cost you anything. It maxes out at about 1,300 people that you could identify. The state of West Virginia is a great example of why you really have to consider the context. One person was estimated to be unique or identifiable, and it would have cost me $17,000 to identify that person. So if I'm an adversary, first place that I'm going to go for data is probably, Virginia, or maybe South Carolina. Sorry, Indiana, you guys didn't make the list. So I actually wanted to point to something that was published last week. The U.S. Department of Health and Human Services issued a challenge a couple months ago. They said, you know, all these people are saying that data is identifiable. We don't believe you. Prove to us that it is or it isn't. So what they did was they gave 15,000 safe harbor records to a team at the University of Chicago, specifically at Newark. They said these are people who were self-identified to be a minority. So this team went off and they purchased a lot of public records. And at the end of the study, they were able to identify 2 people. Okay? In other words, about, what is that? That's less than 0.01% of the data set. Yeah?
Were they restricted to using purchased public records?
They were allowed to use whatever they could get their hands on without needing special credentials.
So like the Facebook screen thing that dumped on.
They could use Facebook if they want to.
So,
And there's another study that's coming out of Canada that shows how they did use Facebook to identify someone. But again, the number of people that they could identify was extremely low. And in fact, most of the data on Facebook is not very reliable. So
no, I was just curious.
yeah, so people are using all different types of things. Yes, if you want to try and replicate the study, please do. I would love if somebody did it.
So,
Yes, I had a question.
so did they define what public data they use? So besides I assume voter registration.
They actually went to Info USA and purchased all the data on 35,000 people who were in the same region as these 15,000 people. So if you want to know more about the study, I'm not going to talk about it. So go back and look at this presentation by Deborah Lafke. Okay, so that's a little bit about measurement. Let's talk a little bit more about mitigation. So I want to shift perspective. So we've talked about the identification from safe harbor. What's this notion of expert determination methods? So this is what it says in the regs. It says that you have to certify via generally accepted statistical and scientific principles and methods that the risk is very small that the information could be used alone or in combination with other reasonably available information by the anticipated recipient to identify the subject of the information. Don't you love lawyers? Yeah, I wish. Joke doesn't work as well. So several things.
Bread.
Risk is very small. What?
I said we still have bread.
Oh, I love bread. The risk is very small, and you have to identify the subject. And the other thing is that you have to use reasonably available information. So it does not matter if the data is identifiable per se. You still have to show that you used reasonable methods and reasonably available information. And I'm not here to say whether or not this should be the regulation or not. I'm just telling you what the current regulations are. The other thing I've always found intriguing is that you have to care about the intended recipient. So one thing that we've been looking at recently is how to push this type of a model into an expert system, or try to come up with expert models for de-identification. The studies I've shown you so far have been about populations, but we wanted to look at specific sample data sets that we wanted to disclose. So this is a paper that's coming out next month. Basically what we do is we take a sample, we subject it to the safe harbor procedure, we take out the safe harbor cohort, and then we use our risk estimation models using population counts or anything that we've got to try to figure out how risky it would be to share that data set. And then we have a set of risk mitigation procedures that say I'm going to share data sets that have risk that is no worse than what I estimated for safe harbor, and that's what we're going to call a statistical standard cohort. And a little bit of an example of how we do this with demographics. I'm not going to have time to go through how this all works, but basically what we do is we model all policies on a lattice. And then what we do is we'll show that safe harbor is one of these policies, okay, where what you're looking at here, I should have given you a little bit of context, is that these bit strings correspond to how much generalization we've actually put into the system. So imagine I gave you names, genders, ages, and diagnoses. We're going to play around with the gender and age in this context. So if I set everything to all zeros, that means that everybody has been grouped together. So male and female, it's ambiguous. The age has been grouped to 20 to 24. In this model where we've allowed for some more specificity, this first bit said, look, let the gender be in its most specific state, split the age at 22. So 20 to 22 can be grouped together, 23 to 24 can be grouped together. And then there's other policies out here. So basically what we do is we can show that risk is monotonic on this graph, and then we can start intelligently searching this graph for points at which the risk is no worse than safe harbor. So if I said safe harbor is at this point, I can start with a random seed, and then I can basically use a bisecting search strategy to try to find something that's acceptable. So if this risk, for instance, is no worse than this guy, then I know that, or I have a potential that one of his children would also have risk that's no worse than this guy. So I can search down, at which this one might not be acceptable, at which point I then have to propagate back up. And I might find a policy that says, data is generalized in a completely different way than what you would get with safe harbor, and the risk is no worse.
But in this situation, have you guys considered the utility of data?
Yeah, we have, and I'll show you actually why we did it this way. So here's a case study. This is a cohort of 3,000 patients from Vanderbilt. One of the reasons that we looked at it this way was because we wanted to have age in a more specific state, because safe harbor says you can't give out these people. These are guys who have age over the age of 89. We're not messing around with anything except the demographics. But so here's safe harbor. So we didn't do anything to gender. We didn't do anything to race. Null here, it means we didn't change anything. And the risk was that one of the people here was expected to be identified. So here's several alternative models that the approach would discover. One said, look, well, you can generalize gender, and then you could have age back. Okay, but you don't get gender, and in the context of a genome-wide study, chances are you're going to know the gender anyway. But here's one. So we could allow for gender. We could put the Asian subpopulation with the other ethnicities, which were people who there just weren't enough of them to really justify reporting their demographic. And then we, again, could have all the ages back again, and the risk, again, is no worse than safe harbor. Here's one where you get gender, you get all the races, and instead of telling you the 52 and the 53-year-olds, I tell you it's the 52 or the 53-year-olds. Okay. Now, searching this lattice can actually be done relatively efficiently to find good policies. Our approach basically was able to find about 100 of these nodes in about 8 minutes. If you use a naive search strategy, it takes about 1.5 hours. This is the obligatory my algorithm is better than your algorithm graph for all you database researchers. But let's look at a bit of a broader case. So the one that we were really interested in, so these are all of the eMERGE data sets. So these are the primary phenotypes that people are studying. These are some quality control phenotypes. The reason why I say this is primary phenotypes were dementia, cataracts, peripheral arterial disease, type 2 diabetes, and QRS duration. That's the one that we do. Northwestern was running our phenotype, and Vanderbilt was running Northwestern's phenotype. Now, all different states, different state populations. This will just be to represent the data set. And these are the sizes of the data sets. The intriguing part is that Group Health had a data set in which almost half of their population were over the age of 89, and they were constructing regression models. So if you truncate that distribution, you're going to have a bit of a problem on your hands. So we wanted to see if there were alternative models that we could use. So rather than search the lattice, we defined some very simple policies. So this was safe harbor. Generalized ethnicity. These were the ethnicities that we had available to us. So you've got, these are the other groups, so American Indian, Asian, Native Hawaiian, some other stuff. The two primary ones were African American and white. So here's the policies we played around with. Generalize the ethnicity, generalize the age to 5-year bins, 5-year bins and generalized ethnicity, 10-year bins and 10-year bins and generalized ethnicity. And this is basically what you're looking at. So these are a couple of the policies, and this says the risk was no worse than safe harbor. This says that the risk was worse than safe harbor. So one thing that we found was that we could do age of 10-year bins for group health, but some of the other policies didn't work out for them, these simple policies. But for everybody else, we were in a pretty good situation. All right? So even though they had people that could not be shared according to the safe harbor, we're basically showing you could share them. All right, so a couple of notes, and I'll stop. So one thing is that what I showed you was a very new, crazy idea in terms of how you would generate a de-identified data set, because we basically said it's okay to leave uniques in your data set because Safe Harbor is already doing so. Right? You don't necessarily have to allow for that to be a solution. One principle that you could try and apply is what's known as k-anonymization, which would guarantee that every record that you share has at least k-1 other records to which it's equivalent. Necessarily advocating for that or not advocating for it. I'm saying you could try and apply it. If you want to know more about that, read that paper. There are other routes for re-identification, but I would really say that we can prioritize, model, and mitigate those as necessary. And we can actually consider solutions that merge security and privacy. So currently what I'm showing you is that we just put the data out there in its most plain text form. We've been playing around with models that are more cryptographic in nature that says, I don't necessarily trust the person that I'm giving the data to, so what if I stored that in an encrypted way that allowed them to run queries over it such that you could get aggregate results without seeing what any particular record has? That's a different model that you could try and apply. There are some open challenges. So first of all, this is more of a policy call. It takes a lot of time, not necessarily a lot, it takes some time and energy to appropriately model these risks. But I would say that you can and should do it, but to do so on a large scale, we need to figure out what experts are. We need to train them. So one of the biggest problems with HIPAA today is that it says you get an expert to come out and certify your data set and say that it's a non-risky data set. Nobody has any clue of who an expert is. There is no CISSP model, there is no certification model to say who these experts are. It basically says, go find a statistician, go find a computer scientist, go find the hobo in the backyard. It doesn't say that, but I'm just saying there's nothing, well, I'm on television. It just, there's nothing that says who these people are. One thing that I've been trying to advocate for recently, the Center for Democracy and Technology has been chiming in on this as well, is that maybe what we need is a national center of excellence, similar to the way that the NSF funds centers of excellence for, like crystallography or supercomputing. It would be nice if we had some type of a model, especially if this is a much broader problem than healthcare. Okay, if we're just talking about sharing of data, and we want to talk about identifiability of data, it would be really nice if we had some type of place where there's some centralized brain trust that you could rely upon. Maybe something similar to CERT. I don't know. So some of the things that we haven't addressed yet, but are still open problems that we're starting to look into, longitudinal data sets, that's a big problem. Multiple data sets, what happens when I've got a patient record represented in different ways in different data sets? That's an issue. That's known as being subject to intersection attacks. We also have to determine what an acceptable level of risk is. And I would argue that this is dependent upon the type of data that we're talking about. However, the federal regulation doesn't make a distinction between types of data. So if I've got a data set that corresponds to HIV positive patients, chances are that's going to be a little bit more sensitive than if I got a data set of people with broken left toenails. I'm just speculating here. I might be wrong. But currently, the federal regulation doesn't say anything about the type of data, and they're not going to draw that line in the sand. But we probably need to. It's also going to depend on the type of person that you're giving data to. What we've seen is a two-party model, or a two-structure model, where we've got people who sign a contract and people who don't sign a contract. Maybe we need to have different types of data set for public health and clinical research and different types of entities. I'm not trying to make the system more complex. I'm just trying to offload some of the computational responsibility towards contractual or social-based agreements. So it's also going to depend on the organization and their capabilities. So a couple final thoughts. Privacy risks are highly, highly contextual. One of the reasons why I spend most of my time in a medical school is because the challenges that they face are very much dependent on the semantics of the data and the needs of the data sets. They're one of the places that they actually have privacy legislation that talks about identifiability. I don't know if they're going to end up leading the charge for the other domains, but they're definitely publishing more papers on the topics than anybody else. So these risks really do need to be quantified. Otherwise, you end up with federal blanket policies like Safe Harbor that leave different states' data subject to different levels of risk, which is really just almost mind-boggling in certain respects. And in a sense, I'm not necessarily going to say you have to do this, but these solutions would really benefit if they're multidisciplinary. So, for instance, if you've got a computer scientist who is sitting in a room all day long and they're building a really fancy schmancy algorithm and they haven't talked to the clinician who's actually going to be using the data, chances are the algorithm at the end of the day is not going to be what they want. Similarly, you could end up designing an algorithm that's illegal to use. Right? So I'm not saying that you should stop trying to develop such an algorithm. It would probably be better that instead of circumventing policy, you would nudge policy a little bit. I would recommend people look towards that gray space. What's reasonable? Who's the anticipated recipient? And try to design things that say, let's try to give a little bit more definition into the space. We've got some wiggle room. Okay, so I said earlier we can't manage what we cannot measure. Basically what I've shown you is that we can measure it. We just have absolutely no idea how to manage it right now. So please do. Some acknowledgments. What's interesting to me is that a lot of the analysis and a lot of the work that I showed you was done by somebody who had just finished their undergraduate in my group. And they were just working as a staff programmer for the last 2 years. So I think that was actually pretty cool. A lot of this work was funded by the National Human Genome Research Institute and the National Library of Medicine. And if you got any questions, you can either send me an email or go to our website. I'll stop there.
Brad.
Oh, perfect. 1 minute.
Wait, one question.
Yeah.
I think Chopin asked about utility. Have you begun to explore any utility functions of the data, or work with some of the clinicians or people who need to actually query within this space?
Yeah. So one of the other things that we work with. So the demographics are they're not. They don't have. There's not as much of a problem with sharing the demographics from a utility perspective. Those models are pretty. The models that they use for normalizing data against demographics are pretty coarse. The challenges are when you start giving out or trying to anonymize the other features that you share. So, for instance, diagnosis codes. So diagnosis codes, what we ended up doing was we constructed a set of utility functions based on how people were trying to use that data and the types of correlation studies they were trying to do. And so we ended up showing that you could still do validation of a certain set of GWAS studies or genome-wide association studies for like breast cancer, colorectal cancer, and we defined all of those policies and baked that into the algorithm that we used for anonymization such that we could keep it goal-oriented. And in that respect, we still had people sit down and say, yeah, the data is still good, the statistics are still going to be sufficient for our studies. So none of this stuff talked about the clinical utility, but yeah, we looked into that.
Okay, so have you published some work on?
Yeah, there was a paper that was in Proceedings of the National Academy of Sciences back in April this year.
Okay.
There's a lot of media attention on that one. We also showed that you can extend the algorithm and you can support query response or query answering for things that were not in the utility function. And we showed what the rates of error were for that. And in some cases, it wasn't too bad. It was still within a bound of like 1.5, the original answer.
Just also a question related to Rebecca's question. And then you talk about very interesting model. You have analysis, and given a policy, a certain kind of, privacy guarantee, right? And then looking at, whether you can come up with another policy equivalent or even better, a privacy guarantee. So, I'm just thinking about, maybe a little bit crazy idea is, instead of talking about, privacy guarantee, so how about we just talking about utility? So given a specific utility, so the question becomes, so what kind of policy you can come up with, and in other words, what kind of privacy you can guarantee?
So the way in which the research I didn't talk about today, the way in which we solved the problem is we actually Malin is a dual optimization. So we search that privacy utility frontier, and we look at the trade-offs between the two. If you only look at one and then try to satisfy the other one, you're kind of shining a flashlight looking for your keys. You don't necessarily know what the results are going to be. You're better off trying to optimize the whole system. And the funny thing is that the statistics community proposed this model like 15, 20 years ago. So there was a model that was proposed by George Duncan, who was at CMU, called the RU confidentiality map, where the R stands for disclosure and the U stands for utility. And they showed that there are certain types of functions that you can't find in that frontier. Some of this stuff, it's a really complex frontier. So I don't know if you can always do it in that way. But
alternatively, you always can format price security guarantee you want to achieve, and and the utility as two constraint. Then you're trying to search under these two constraints to see if it's feasible.
Right. And it's either going to spit out that's feasible or it's infeasible. Or it's stuck in a non-solvable environment. But I agree. You can go in either direction, or you can do both at the same time. It depends on the complexity of the space. Yeah.
Do you have any idea how, instead of a system identifying, maybe I have a near identify, how that trades off from your risk? So, I mean, it seems to me in certain cases, I don't, identifying me is bad, but if you put me in a group of 1 in 100, that might be just as bad.
Correct.
And,
Yeah, but that's why that's up to that. So the risk results that I was showing you included the people who were in groups of 100. So
but what I'm asking is, like, do you have some sort of formulation of how you specifically trade off the group size?
yeah, we do. So that's actually a paper that's coming out in a couple months. Let me see if I actually have the equation. Yeah. So we actually formally model that trade-off where this is the group size. This is actually a dampening factor that you can use to control how much a particular group size ends up influencing the identifiability of the system.
Is